Good morning, I'm Professor Uniqueness, and this is the first of 3 videos discussing common proof approaches or techniques. So as you watch these videos, there are 3 takeaways I hope that you will get. The first is I hope that you will recognize the underlying logical equivalence or structure that justifies the given approach. Why is this a valid approach? The second is understanding the structure of the approach. In particular, each approach sort of designates what your needed assumptions or premises are and what the desired conclusion will be. So the start and the end of a proof will be determined by the approach you use. So recognizing that structure for each approach. And then finally, I would like you to gain from these videos a start of a sense of what statements are best aligned with a given approach. So each approach has a particular set of statements that it might work better for or worse for. So recognizing that matching. So there's the quote that, the fields of observation chance favors the prepared mind, or Einstein's quote, a new idea comes suddenly and in a rather intuitive way. The intuition is nothing but the outcome of earlier intellectual experience. So as you have more experience proving things, identifying which proof approach to take is going to start to feel intuitive, but really it is just learning these sort of statement types or structures that pair well with a given proof structure. So we're going to start looking at some of the more global structures. And what do I mean by that? As you prove things, you'll find that many proofs are going to involve multiple proof approaches. Usually the structure of a proof will be some sort of global structure or some global approach, and then nested within that larger proof will be sort of mini proofs that might have a different structure or a different approach. But the techniques we're going to start with are the ones that are most likely to be that global approach, the sort of large scale approach, which has to do with how you view the statement. So as you read a statement, there's sort of the mile-high view of the statement, and then you can dive into the component pieces of the statement and what their structures are. So these approaches often apply to that kind of mile-high view. All right, without further ado, we'll jump. So the first proof technique we're going to look at is proof by contradiction. It's one of the most common proof approaches. We'll talk at the end as we look at an example of why that is. But as we'll see, in large part, it's because it gives us the most assumptions at the start. So we have the most to work with, and the desired conclusion is any contradiction. So we kind of have multiple potential endpoints. And so this often makes the proof easier than if we were starting with a smaller set of assumptions and had a very particular endpoint we were going for. Proof by contradiction is based on bivalence, or the law of the excluded middle, and the idea that a statement R is either true or it's not true, and that if you can prove that it is not, and if you can prove that you do not have it being not true, then it must be true. Another way of saying this is the equivalence of the double negation with the original statement. And that's how we usually think of it. So we're basing this proof technique on that double negation principle. And so what you're going to do is you're going to show that not R is false. So the structure of the proof goes as follows. Proof by contradiction. Just as a note, for this video, I'm going to use shorthand and abbreviation and logical symbols, but of course, if you're writing a formal proof, your proof should be in complete grammatically correct sentences. So how does a proof by contradiction go? Well, if we're trying to prove the statement R, we're going to suppose, by way of contradiction, not R. And we just need to show not R is false. So we can create our chain of logical implications and equivalences, giving mathematical justifications as we go until we reach some sort of contradiction. So here's my contradiction symbol. Some people use an X, but it's basically the idea that you have concluded something that is clearly false. And thus, it must be the case by modus tollens, if not R implies some statement, let's call it Q, and we know that statement is false, so we know not Q, then by modus tollens, we have not R, or the equivalent R. So having concluded something that is clearly false, we would say, thus, it follows R must be true. And then we would finish our proof with our little ending proof note or QED. I like to do the black box because I kind of think of it as like a microphone drop. It looks like an ice cream cone, but we get the idea. All right, so another thing just to remind you that as you write your proof, while I am pointing out in this video the sort of logical structures behind the proofs, you would not state those in the proof. Within the proof, you're only going to use mathematical justifications to justify each step. The next sort of global proof approach we're going to look at is how do you prove for all statements? So this is based on the logical structure of universal generalization, which says that if you have some statement P involving the variable A for some arbitrary value A in your set U, if you know that that statement is true for an arbitrary A in U, then you can universally generalize to say that for all elements of the set U, this statement is true. And so how does this manifest in a proof? We are going to instantiate an arbitrary variable. So let A be an arbitrary variable, an arbitrary element, I should say, in the set U. And the notation I use for that, just shorthand, is this AE in U. So A is an arbitrary element in U. If you can then prove, and I got tired of writing the link, so I'll just do a line for kind of the part of our proof that's going to be some sequence of logical implications and equivalences with mathematical justifications. If you can show then that the statement P of A is true, then by universal generalization, it must be true for all elements of U. Now again, in a mathematical proof, we wouldn't say by universal generalization. We normally just say, since A was arbitrary, it follows that the statement P of X is true for all X in the set. The next proof approach we're going to talk about is the proof approach for existence statements. How do you prove that there exists a particular element in a set U such that the statement P of X is true? And this is based on the logical principle of existential generalization, which says that if you know a statement P of B is true for some particular value of the set U, then you can generalize that to say that there exists an element in the set such that the statement P of X is true. Right? So we just need to verify that the statement is true for a particular X. Now, how do you do this? This is one of, this proof approach is very different than most proof approaches because something kind of magical happens. You basically introduce your X. So in your Scratch work, you find a value of x in U such that P of x is true. And then you just introduce it into your proof. So your proof will start something like, consider this value of x. So let's say you find your value of x such that P of x is true, and that value of x is b. I'll call that value xb. So consider the value b, and you're going to need to prove a few things about that value. You're going to need to show that b is actually an element of your set. This might be obvious, right? If your set is the set of all integers and the value that you found is 2, you don't need to take much time to show it's an integer. You should probably just state, note b is an integer. The next thing you want to show is that the statement P of b is true. And then once you get those two things, that this one, might take some work. There might be a chain of logical implications and equivalences that get you there. So maybe I'll try and make my notation show that a little bit better. Once you have that chain of logical implications or equivalences that imply that P of b is true, then you can just say, thus, there exists an element in the set U such that the statement is true. And again, microphone drop. So the thing about existence proofs is that this scratch work we're doing here often looks backwards. We often start by assuming an x exists with the desired properties and then solving for it. So for example, in this proposition, we're going to assume that we have some x whose square is 3 more than 5x plus x over 2. In other words, we're assuming that there exists some value, some value x whose square is 3 more than 5x plus x over 2. Okay, so now I'm just going to solve for x. So if this is true, then I can multiply through by 2 and bring everything to one side of the equation, and I have 2x squared minus 10x minus x minus 6 equals 0, or 2x squared minus 11x minus 6 equals 0. And by the quadratic equation, that tells me that x is going to be 11 plus or minus, right? We know it's negative b plus or minus square root of b squared minus 4 times a times c divided by 2a, or 4 in this case. And so that gives me x is equal to 11 plus or minus, let's see, 121 plus 48, so square root of 69, so 13 over 4. And so the two values here are 11 plus 13, 24 over 4, 6, or minus 13. So 11 minus 13 is 2, negative 2 over 4 is negative half. Okay, but we see only one of these is an integer. So only the 6 works for this proposition, and that's fine. Here in my proposition, I would say something like, consider x equals 6. Clearly, 6 is an integer. Note, 6 squared equals 36, and 5x plus x over 2, or I should say, 5 times 6 plus 6 over 2 is equal to 33, which is 3, I suppose, less than 36. Therefore, 6 is an integer such that 6 squared is 3 more than 5 times 6 plus 6 over 2. Okay. Thus, we can show that there exists some integer such that the statement is true. Okay. probably could have worded that a little bit better, but hopefully you get the sense. Another type of statement that we're often asked to prove is that not just that there is an element in a set U, but that that element is unique. So we often see examples of statements that are of the form, there exists a unique X in the set U, such that P of X is true. Now, such proofs are going to involve two parts. You're going to have to first show that there exists an X in U, and then show it's unique. So we've already talked about showing that there exists an X. Well, that's what we've done right up here. We want to focus on the idea that it's unique. How would we prove uniqueness? And there are two approaches to proving uniqueness. So the first would be to assume that there are two elements satisfying the predicate P of X. So suppose, let's do this in blue, that's what I've been doing these in. Suppose that the statement is true for both some element A and some element B. So you're going to suppose the statement is true for both of those. And you're going to show that just that assumption is enough to conclude that those two elements must have been equal. So if whenever the statement is true, the element for which it's true is the same, then there is a unique element. So therefore, P of X is true for unique. Well, actually, we haven't shown existence, so we should thus say, therefore, if P of X is true for some element in U, that element is unique. An exclamation symbol is the mathematical shorthand for uniqueness. Okay, so this was option one. Okay. Option two is we could do proof by contradiction. It's really not anything different than a contradiction proof. But let's talk about what that would be. So we are going to suppose the negation of our statement R. So here's my statement R. And so we are going to suppose not R. What is not R? Statement R is saying that it's a unique X in U such that P of X is true. So not R would be that there exist multiple X such that P of X is true. Multiple distinct, I should say, right? It's kind of implied in the word multiple, but let's just make it clear. So how would that proof structure go? We're going to suppose that A does not equal B, and P of A and P of B are true, and show somehow that that assumption has led to a contradiction. Okay. So thus, having reached a contradiction, it must be that if, therefore, this is the symbol for therefore, if P of A and P of B are true, then A equals B, and once again, we can conclude that the statement has to be true for a unique element. Okay, so that's proving uniqueness.